So now that we have a complete understanding of which elements are invertible mod n, we can now completely describe affine encryption in any modulus you want. We spent half the semester working mod 26 just because it's fun to talk about English messages, but we don't have to. What if we want to work mod 39 or mod 1004? So here's how it goes. What we're going to do is we're now going to talk about how you have affine encryption functions mod n, where n can be whatever you like. So our alphabet is going to be, in that case, the symbols 0 through n minus 1. Just like when we worked mod 26, we had symbols 0 through 25 that we secretly thought of as A through Z. Okay? So these symbols 0 through n minus 1 are going to make up our messages. And as before, an affine function is just one that looks like a straight line, mx plus k. And m and k are constants, and of course m is going to end up being called the multiplicative key and k the additive key. Okay? So before we do that, we have to know which of these functions can actually be used to encrypt. Remember, we can't use a function if it sends two different plain symbols to the same cipher symbol. That's called a collision, because then Bob can never decrypt. So the question is, which of these affine functions are actually free of collisions, also called one-to-one in mathematics? So which of these are one-to-one functions? So the first theorem tells you the answer. It's the same answer we had mod 26. Consider the mod n affine function f of x is mx plus k. Then I claim that f is collision-free if and only if m, so the multiplicative coefficient, is invertible mod n. And so here I give a little argument as to why that's true. And this is exactly the same argument I gave in class when we were working mod 26. Okay, so I gave an argument in lecture for why is this true mod 26. It's actually the same exact argument. Okay, so now we know exactly when we can do this for affine encryption. Okay, so the question is, we now know that in order to use a multiplicative key m, that m must be invertible mod n. It must be a unit mod n. But you also know from what we know about Bézout's theorem that this is exactly the same thing as asking that the GCD of the multiplicative key versus the modulus ought to be 1. In other words, your multiplicative key and your modulus must be relatively prime. Just like mod 26, there's no restriction on the additive key. So here's the verdict. You can use this affine function here with key mk, and that's valid for encryption if and only if the GCD of m and n is 1. It has nothing to do with k. Right? So there we go. That's how you do affine encryption. The keys for affine encryption are ordered pairs. M, the multiplicative key, and k, the additive key, where m has to be invertible mod n. Okay, so here's an example. A natural thing to do is to work mod 10, because if we work mod 10, our alphabet is the digits 0 through 9. And these are exactly the digits that we use to make up any ordinary everyday number. We use digits 0 through 9. So if you're going to do affine encryption on this alphabet, the function 3x plus 8 would be valid because 3 is a unit. 3 is invertible mod 10. You can check that its inverse is 7. So that's a valid function. G of x being 4x plus 9 is not, because 4 is not invertible. The GCD of 4 and 10 is 2. That's not 1. So you could not use this, but you could use that. Suppose we wanted to use that function. Excuse me. We want to use the key 3, 8. So 3x plus 8 is our function. Here's what the cipher table would look like. Our plain text digits would be 0 through 9. And here's what the cipher equivalence would look like. So for instance, if I take 2 and plug it in, I get 3 times 2 plus 8. That's 6 plus 8. That's 14. But 14 mod 10 is 4. So 2 would map to 4. Okay? So here's how you would fill out the encryption table for your alphabet 0 through 9. And notice that this is in fact collision free. There are no repeats on the bottom row. So whatever Bob receives, he can always go backwards and decrypt. Okay? So for example, what if Alice wanted to use this function and encrypt the plain text message 44278? Well, the 4 would encrypt to a 0, so that's the zeros there. The 2 that she uses here would encrypt to a 4. The 7 would encrypt to a 9, and the 8 would encrypt to a 2. So her ciphertext is 00492. And of course, Bob can decrypt this because the table is collision free. When Bob sees that 9 right here, he knows that 9 really came from a 7. So he knows it's a plain text 7 in that position. So this works. This completely works. So here are 2 problems for you to do in a Canvas quiz. Let's work mod 10. And Alice is going to choose to use key multiplicative 7, additive 2. Take the plain text message 471 and encrypt it for her. What's the ciphertext? The ciphertext will be another 3-digit number. Just plug it into Canvas. In exercise 2, it's a little bit more work because you're Bob. I changed the key. Now the key is going to be multiplicative 3, additive 4. But now you're Bob. So Bob receives a ciphertext message 9134. Decrypt that for Bob and get the plain text. And just plug in that 4-digit number into Canvas. So that's how Affine encryption works. So now we have a question, and you knew this question had to happen, which is, how many keys do we have? You know that has to be the very first question that you ask about any encryption scheme, because you want to make sure you can measure that scheme's security against brute force. So how many keys do we have? Let's do mod 10. If we work mod 10, you know that keys come in 2 parts, the multiplicative part and the additive part. Certainly for the additive part, you can choose 10 things. There's no restriction, anything 0 to 9. So there are 10 choices for how you choose K. But the question is, how many ways can you choose what you want for the multiplicative key? Well, remember, we're not lost here. We know the answer. We know we have to have the GCD of M and the modulus, which here, the modulus is 10. The GCD of M and 10 has to be 1. So just work out which of the M's make that work. So my M's can be 1 through 9. Notice that 0 is never going to be invertible. You can never divide by 0, so to speak. So out of habit, I never check it. So I check 1 through 9, take the GCD. The GCD of 1 and 10 is 1. That counts. The GCD of 2 and 10 is 2. That doesn't count. The GCD of 3 and 10 is 1. That counts. The GCD of 4 and 10 is 2. That doesn't. I'm looking for the GCD to be 1. So just do it for the whole list. You see that who has GCD 1? 1 does, 3, 7, and 9. So there are 4 yeses here. So there are only 4 invertible elements mod 10, 1 and 3 and 7 and 9. So there's only 4 things you can choose for M. So how many keys are there altogether? There's 4 ways to choose a multiplicative part. There's 10 ways to choose the additive part, so there's 40 keys. So there are 40 affine keys when you work mod 10. That's awful. That's awful. But you should expect that because there's 312 keys when you work mod 26, and we've known that for over a month. So working mod 26, you get 312. You should expect there to be fewer keys when you work mod 10, and in fact you do. There's only 40. So what I want you to do now is do this 2 more times. See how I made this table to keep track of what I was doing? Do it again and do it mod 12, and do it again for exercise 4 in the Canvas quiz, and do it mod 13. How many affine keys are there? You got to first work out the number of multiplicative keys, and then you know the number of additive keys, multiply them up, and you're done. And what I want you to do, what I want you to notice when you do this, is that something really interesting happens with 13. Okay? See if you can spot what it is, think about why it happened, and we'll take it up in the next handout.